Hello everyone, welcome to the session. So in this particular video, we will start our new module of data structure, which we called as a queue. So let's get started. We'll see that how basically we can do the implementation of queue via an array-based data structure followed by a linked list, right? Just like the way we did in our stack-based data structure as well, right? So let's get started with the queue data structure. Fine, queue data structure. So this word queue, whenever we used to listen, one thing I think everyone have in their head is a long queue, right? For example, we are going to a railway station and we want to book a ticket physically. So what we usually have a long queue, which we usually see in our railway stations, right? And those who are coming at the very first will get the ticket also at the very first. So their first come, first serve basis tickets will be allocated, right? So this is something which we have in our data structure as well. So queue basically implements the algorithm called as FIFO. So there is an implementation of FIFO. The full form of FIFO is first in, first out. So if you remember when we were talking about the stack-based data structure, at that point of time I told you that stack implemented LIFO, last in, first out. So whichever is going last will come out first. That was the implementation of stack. But queue example you can relate with the real life also. Whichever will come first, for that person only ticket will be allocated firstly. So here first in, first out type of algorithm will work internally whenever we are talking about a queue. So here what will happen is that, suppose this is the queue that we have. In this queue there is a front side where the deletion will happen. So there is a front side in a queue where I would say deletion of an element will happen. And then there is a back side which we called as a rear side, where usually the insertion of an element will happen, right? So again, if someone is asking to you, what is the ADT, abstract data type of this queue-based data structure? So what is the meaning of that? The simple meaning is that we want to understand that what do you think is the common operations that we have inside this queue-based data structure that we have. So the answer should be that ADT of this queue-based data structure will be something which is either it will be NQ or it will be something which is equals to DQ. NQ means that we want to do the insertion of an element, right, inside the queue. So insertion of an element inside the queue is NQ. And when we talk about DQ, it is something which you can say is the deletion of the elements. So whenever we do the insertion, this is called as NQ, and whenever we are doing the deletion, it is called as DQ. And this is something which you can say is the abstract data type of the queue-based data structure that we have. Okay, now if this is fine, let's talk about that how basically the operation of NQ and DQ will be done. As I told you that there are two things that we have here, which is called as front and the rear. So whenever we are talking about insertion, the rear factor will get updated, and whenever we are talking about deletion, the front factor will get updated. So here let's talk about the insertion, or what we can say NQ, using the arrays. So again, whenever we are talking about a queue-based data structure, just like the way we have understood for the stack, there are two ways to do the implementation. One is with the help of an arrays, and another one is with the help of a linked list, right? So this is something that we have inside the queue-based data structure. Now, whenever we are doing the implementation using arrays or the linked list, what's the, I would say, pseudocode or the logic behind using the NQ is what we need to see next, right? So what is the logic behind that? So what we are trying to do here is that obviously we are trying to initialize the values of front as well as the value of the rear with -1. So it simply indicates when the value is initialized with -1, it indicates that initially your queue is empty. Means you will not be having any single element inside the queue. Now suppose you want to insert any element. So what you will try to do is that, so you will try to create one function called as enqueue, and here you want to suppose insert the data inside the queue. So what you will try to see first, you will try to see that is the value of rear is equal to the value of n-1, means whether the size of the queue will get exceeded or not. If yes, this is something which can I say is a condition of what we can say as queue overflow, just like the condition that we have seen for the stack overflow, right, in our last classes. So this is where I can say that queue is fully filled, can we say, at that point of time. And when it is fully filled, and if you want to insert further more element inside that, that is something which you can say is a condition of, I would say, queue overflow. If suppose that is not happening, in other case, what can happen is that it might happen that the value of the front and the value of rear is something which is equals to -1. Means both of these values is -1. It simply indicates that the queue that you are trying to insert is empty. Can I say? As I told you that at that time only, these two factors will be -1. So at that point of time, you can simply update the value of queue as well as update the value of the rear, and you can simply try to insert the data, right? You can simply try to insert the data. So for example, here you are taking the queue and the data. So you can simply try to insert the data at the rear part. Queue of rear is equals to data. In else part, it simply indicates that the queue is not fully filled. Queue is not empty also. You can just try to update the value of the rear by 1, and you can simply try to, insert the data inside this particular queue. Simple. So basically, if you will try to observe here, we are trying to see three conditions. First condition is whether the queue is fully filled or not. What is that condition? We will try to see the size of the element. Usually in Python, because we will be having the concept of dynamic array, so this thing might not be valid. But for other programming languages, this thing will be valid. So that's why I am writing a common pseudocode for all the languages. So that is the condition of queue overflow. If suppose that is not happening, then we can look for the condition of the empty queue. What will happen when the queue is empty? At that point of time, we all know that the value of the front and the value of the rear will be equals to -1. So at that point of time, when you have the very first element, your value of the front will be equals to plus. You will need to upgrade the value of front as well as the value of the rear. And if suppose you are not dealing with the empty queue, or you are not dealing with a fully filled queue, at that point of time, you just need to upgrade the value of the rear pointer, and you can simply insert your data inside that. Here, if suppose I will talk about the time complexity part. Now, what do you think should be the time complexity of this insertion? Here, if you will observe, I am doing simple if and else condition, and according to that check, I am just trying to do the upgradation of the pointers and will try to allocate the values inside the queue. So here, if you will observe, we are not doing anything so-called unique where we are applying any sort of for loops or we are doing something big. So what I want to say here is that if you will observe, the time complexity requirement is big O of 1, or you can say is the constant time complexity. And that is the similar time complexity that we will be getting when we were talking about the insertion inside the stack as well, if you remember, right? So this is what we have in case of enqueue data, enqueue in case of a queue-based data structure. Now, the next important part which we want to see here is the concept of dequeue. So what will happen in dequeue? In dequeue, again, if you will observe, we will be having the data, right? And we will be having the value of queue. So this is the original queue that we have. And then we will be having the data here. Now again, if you will try to observe, if suppose the value of the front, the value of the rear is equal to -1. Again, this is the condition where I can say that the queue is empty. Can we say? And if the queue is empty and you want to delete any element, this is something which we can say is queue underflow. Can we say? Right? Because you want to delete something which is not already present inside your queue because the queue is already empty. So this is the condition that you can say is the queue underflow condition. Queue underflow condition. If that is not the scenario, in that particular case, what will happen is that you can simply try to do one thing. In ELIF, you can do one thing. If suppose the value of the front and the value of the rear both are equals to +1 only, it simply indicates that inside your queue you will be having single element. Can I say you will be having a single element? Can we say that or not? So in that particular case, what we can try to do here is that we can simply try to, upgrade the value of the front. Can I say? So if the value of the front and the rear is equal, at that point of time, you can do simply one thing. You can simply try to update the value of both by -1, which simply indicates that, okay, you want to delete only single element which is present inside the queue. And we all know that after deleting that element as well, we will be left with the empty queue. So at that point of time, we can simply, say it as -1. Otherwise, I can do one simple thing. I can simply upgrade the value of the front by +1. Because as I told you that the deletion will happen from the start. For example, let me try to explain to you this point. I have inserted at the very first time 3. So front is pointer is here, rear pointer is here, right? If I am having only single element at that point of time, even you don't need to write the data as well. Only queue part is enough here. Why? Because we are not manually saying that I want to delete that element. Here, whichever pointer will be at the front side, that particular value will get deleted. Now when you insert 4, what will happen? Front will be remaining its own position. The value of the rear will get updated to 2. Now suppose you inserted 5, what will happen? Rear will get updated. You inserted 10, rear will get updated. So now the insertion will happen like that. This is something where if you will observe, I would say NQ type of operation is happening inside the queue. But what we have observed or what we have understood that queue implements the FIFO operation. First in, first out. So I want for sure some pointer to be there at the first element, which is, I can see here, right? At 3, which was the first element I have inserted inside the queue, front is there. So now when deletion part will happen, front will automatically get upgraded to this particular part and automatically this part will be deleted. Automatically I can return this particular value if I want to, right? So this is something that we can do. What you can do here is that you can, if you want to print the data as well, you can say data is equals to Q of F. Initially you can take that data. You can update the value of the F pointer and then you can return that data as well. You can return that data as well if you want. But the important thing here to understand is that what is the intuition behind F pointer? What is the intuition behind R pointer? So here again, if deletion will happen, F will shift towards this. F will shift towards this. So even here, instead of mentioning the value of F and R as +1, it doesn't matter whether it be +1 or not. We should say that when the value of F and R is equal, for example here, again it will go here. Now again if DQ operation will happen, again the value of F pointer will get upgraded and F will point here. It means that automatically all these elements are related and now we are only left with this 10. In this particular case also, this condition will get satisfied and now the value of F and R will become -1. So majorly these are the conditions to delete the element from the queue. And here again, if you will observe, I am not using any kind of a for loop or a while loop. I am just doing a very simple operation of if and else, right? And that's why here also you will observe that the time complexity that we are getting is big O of 1. Meaning, again I can say that here I am getting a constant time complexity. Again here I am getting a constant time complexity. This is the overall idea behind the Q data structure operations. Very important NQ and DQ that you should know, right? How the insertion will happen and how the deletion will happen. The important thing here to understand is that whenever you are encountering a Q-based data structure, a FIFO kind of architecture will come into picture. Whenever this data structure is coming into your head, consider the example of a real life queue in a railway station, in a metro station, anywhere. So just like the way that works, where first in first out will work, similarly this queue data structure will work as well. So whichsoever data will be inserted at the very first end, that data will be removed also at the very first end. That is the overall idea behind this queue-based data structure. And I hope that you will be easily able to get the understanding as well, as it's a very easy kind of data structure, I would say. In the next upcoming video, what we can do is that we will try to do the implementation of the same, right? And with this, I would like to end this particular session. I hope that you really enjoyed it a lot. If you still have any sort of doubt, do let me know for sure. And I'll try to resolve it as soon as possible. Bye-bye everyone. Happy learning to all. See you all in my next upcoming video.